Hello! Today we will explain how magnetic resonance imaging, or MRI systems, use the reaction of hydrogen atoms moving in a magnetic field to yield a detailed medical image. The types of magnetic fields typically used are described. The note explains why today's higher resolution MRI systems rely on superconducting magnets. The note also discusses the formation of 3D images by proper alignment of gradient coils and their interaction with RF signaling. A functional block diagram of a typical MRI system is presented. Magnetic resonance imaging, or MRI systems, provide highly detailed images of tissues in the body. The systems detect and process the signals generated when hydrogen atoms, which are abundant in tissue, are placed in a strong magnetic field and excited by a resonant magnetic excitation pulse. Hydrogen atoms have an inherent magnetic moment as a result of their nuclear spin. When placed in a strong magnetic field, the magnetic moments of these hydrogen nuclei tend to align. Simplistically, one can think of the hydrogen nuclei in a static magnetic field as a string under tension. The nuclei have a resonant or Larmor frequency determined by their localized magnetic field strength, just as a string has a resonant frequency determined by the tension on it. For hydrogen nuclei in a typical 1.5 Tesla MRI field, the resonant frequency is approximately 64 MHz. Proper stimulation by a resonant magnetic or RF field at the resonant frequency of the hydrogen nuclei can force the magnetic moments of the nuclei to partially or completely tip into a plane perpendicular to the applied field. When the applied RF excitation field is removed, the magnetic moments of the nuclei precess in the static field as they realign. This realignment generates an RF signal at a resonant frequency determined by the magnitude of the applied field. This signal is detected by the MRI imaging system and used to generate an image. MRI imaging requires the patient to be placed in a strong magnetic field in order to align the hydrogen nuclei. There are typically three methods to generate this field: fixed magnets, resistive magnets caused by current passing through a traditional coil of wire, and superconducting magnets. Fixed magnets and resistive magnets are generally restricted to field strengths below 0.4 Tesla and cannot generate the higher field strengths typically required for high-resolution imaging. As a result, most high-resolution imaging systems use superconducting magnets. The superconducting magnets are large and complex. They need the coils to be soaked in liquid helium to reduce their temperature to a value close to absolute zero. The magnetic fields generated by these methods must not only be strong, but also highly uniform in a space and stable in time. A typical system must have less than 10 parts per million variation over the imaging area. To achieve this accuracy, most systems generate weaker static magnetic fields using specialized shim coils to shim or tweak the static field from the superconductor and thereby correct for field inaccuracies. To produce an image, the MRI system must first stimulate hydrogen nuclei in a specific 2D image plane in the body, and then determine the location of these nuclei within the plane as they precess back to their static state. These two tasks are accomplished using gradient coils, which cause the magnetic field within a localized area to vary linearly as a function of spatial location. As a result, the resonant frequencies of the hydrogen nuclei are spatially dependent within the gradient. Varying the frequency of the excitation pulses controls the area in the body that is to be stimulated. The location of the stimulated nuclei as they precess back to their static state can also be determined by using the emitted resonant RF frequency and phase information. An MRI system must have X, Y, and Z gradient coils to produce gradients in 3 dimensions and thereby create an image slice over any plane within the patient's body. The application of each gradient field and the excitation pulses must be properly sequenced or timed to allow the collection of an image dataset. By applying a gradient in the z direction, for example, one can change the resonant frequency required to excite a 2D slice in that plane. Therefore, the spatial location of the 2D plane to be imaged is controlled by changing the excitation frequency. After the excitation sequence is complete, another properly applied gradient in the x direction can be used to spatially change the resonant frequency of the nuclei as they return to their static position. The frequency information of this signal can then be used to locate the position of the nuclei in the x direction. Similarly, a gradient field properly applied in the y direction can be used to spatially change the phase of the resonant signals, and hence be used to detect the location of the nuclei in the y direction. By properly applying gradient and RF excitation signals in the proper sequence and at the proper frequency, the MRI system maps out a 3D section of the body. To achieve adequate image quality and frame rates, the gradient coils in the MRI imaging system must rapidly change the strong static magnetic field by approximately 5% in the area of interest. High voltage, operating at a few kilovolts, and high current, 100 seconds of amps, power electronics are required to drive these gradient coils. Notwithstanding the large power requirements, low noise and stability are key performance metrics since any ripple in the coil current causes noise in the subsequent RF pickup. That noise directly affects the integrity of the images. Transmit and receive coils are used both to stimulate the hydrogen nuclei and to receive the signals generated as the nuclei recover. These coils must be optimized for the particular body area to be imaged, so they are available in a wide variety of configurations. Depending on the area of the body to be imaged, either separate transmit and receive coils or combined transmit-receive coils are used. In addition, to improve image acquisition times, MRI systems use multiple transmit-receive coils to recover more information in parallel, thus utilizing the spatial information associated with the location of the coils. An RF receiver is used to process the signals from the receiver coils. Most modern MRI systems have 6 or more receivers to process the signals from multiple coils. The signals range from approximately 1 MHz to 300 MHz, with the frequency range highly dependent on applied static magnetic field strength. The bandwidth of the received signal is small, typically less than 20 kHz, and dependent on the magnitude of the gradient field. A traditional MRI receiver configuration has a low noise amplifier, or LNA, followed by a mixer. The mixer mixes the signal of interest to a low frequency IF frequency for conversion by a high resolution, low speed, 12-bit to 16-bit analog to digital converter, or ADC. In this receive architecture, the ADCs used have relatively low sample rates below 1 MHz. Because of the low bandwidth requirements, ADCs with higher 1 MHz to 5 MHz sample rates can be used to convert multiple channels by time multiplexing the received channels through an analog multiplexer into a single ADC. With the advent of higher performance ADCs, newer receiver architectures are now possible. High input bandwidth, high resolution, 12-bit to 16-bit ADCs with sample rates up to 100 MHz can also be used to directly sample the signals, thereby eliminating the need for analog mixers in the receive chain. The MRI transmitter generates the RF pulses necessary to resonate the hydrogen nuclei. The range of frequencies in the transmit excitation pulse and the magnitude of the gradient field determine the width of the image slice. A typical transmit pulse will produce an output signal with a relatively narrow plus or minus 1 kHz bandwidth. The time domain waveform required to produce this narrow frequency band typically resembles a traditional sync function. This waveform is usually generated digitally at baseband and then upconverted by a mixer to the appropriate center frequency. Traditional transmit implementations require relatively low-speed digital to analog converters, or DACs, to generate the baseband waveform, as the bandwidth of the signal is relatively small. Again, with recent advances in DAC technology, other potential transmit architectures are achievable. Very high-speed, high-resolution DACs can be utilized for direct RF generation of transmit pulses up to 300 MHz. Waveform generation and upconversion over a broad band of frequencies can, therefore, now be accomplished in the digital domain. Both frequency and phase data are collected in what is commonly referred to as the K-space. A two-dimensional Fourier transform of this K-space is computed by a display processor or computer to produce a grayscale image. MRI is often incorrectly considered a superior imaging modality to other imaging techniques. In many circumstances, it is inferior to CT, ultrasound, or even plain X-ray. The successful application of MRI depends on the clinical question in mind and the body part to be imaged. MRI provides exquisite images of body parts that do not move, such as the brain, and anatomical structures that can be kept still, such as parts of the musculoskeletal system. Each set of images produced takes several minutes to obtain. Therefore, MRI is not suitable for patients who are unable or unwilling to remain motionless.